Hi guys, in the last lecture we started with the speed control of induction motor. So we saw that the speed of the rotor is given as Nr is equal to Ns into 1 minus S. So I said there will be two methods to control the speed of induction motor, either by controlling the synchronous speed or by controlling the slip. So first we saw slip control technique. In this, first method was voltage control. So at low values of slip, that is under running condition, we said SV square will be constant because torque is constant. So as voltage reduces, slip will increase, due to which rotor speed will reduce. So this method can be used for obtaining the speeds below rated speed. But here current also increase, so this cannot be used for sustained speed control, that is speed control over longer period of times, because otherwise it will produce heating in the rotor winding which can damage the winding. Next method we saw rotor resistance control. In this we said S by R2 is constant, so S is proportional to R2. So as resistance increases, slip will increase, due to which rotor speed will decrease. This can also be used for below rated speed, but it was only applicable for wound rotor induction motor because we can only connect external resistance at the slip ring terminals in case of wound rotor induction motor. No such facility is provided in case of squirrel cage induction motor. Then we saw rotor EMF injection. In this we injected a EMF at the slip ring terminals having a frequency SF. So if injected EMF has the same phase as the induced voltage, then the total voltage become E2 plus EI. That means it increases, due to which slip will reduce because SV square must be constant, due to which rotor speed will increase. As slip reduces, rotor speed increases. And similarly, if it is in opposite phase, E2 minus EI, that means that net voltage reduces, slip increases, due to which NR reduces. So here we can reduce as well as increase the speed of rotor beyond the rated speed. So it can be used for below rated speed as well as above rated speed. So this is also applicable for wound rotor induction motor. Then we saw pole changing technique to control the synchronous speed. Here we reduce the number of poles to half. So we made synchronous speed to be twice the original value. So rotor speed also increases. This is only applicable for squirrel cage induction motor. Why it is only applicable for squirrel cage induction motor? Because in squirrel cage, as we change the number of stator poles, poles are automatically induced on the rotor. Rotor is not wound with a fixed number of poles. Whereas in case of wound rotor induction motor, the number of poles are fixed even for the case of rotor. So if we change the number of stator poles, we have to change the number of rotor poles also, so that poles on both stator and rotor is same and the motor produces a constant torque. If the poles on stator and rotor is not equal, then there will be alternating torque and motor will not rotate. So remember this condition, the poles on stator and rotor should be same for motor rotation. Okay, so squirrel cage automatically responds to the pole change, whereas wound rotor cannot respond. Hence this method is only applicable for squirrel cage. Next, let us look at the frequency control method. In this method, since synchronous speed is given by 120 into F by P, we can control the frequency to control the synchronous speed. So if we reduce the frequency, then synchronous speed reduces. If we increase the frequency, then synchronous speed increases. If synchronous speed reduces, then rotor speed also reduces. Synchronous speed increases, it also increases. So now first let us look at the reduction in the speed, that is control of the speed below rated speed. Okay, if I want to obtain the speed below the rated speed. Now flux is proportional to V by F. So to reduce the speed, we will reduce the frequency. Flux will increase. Due to increase in flux, flux density will also increase, which can cause saturation. In case of saturation, I mu becomes high. For a small change in flux, that is even if we change the flux by a small amount, change in I mu is very high. Okay, due to which I mu being high, the no load power factor of the machine and full load power factor of the machine reduces. Okay, because the higher the magnetizing current, lower is the power factor. So that is why also due to I mu being high or flux being high, iron loss will also increase, because hysteresis loss is proportional to flux raised to the power 1.6. Eddy current is proportional to flux square. So these are the disadvantages of the pure frequency control. Pure frequency means only controlling the frequency in case of induction motor. So if you just decrease the frequency, the flux will increase, which will cause decrease in the power factor as well as increase in the iron loss. So it is undesirable. So what to do is, we must maintain the flux constant. So by reducing the frequency, we must take care that we reduce the voltage also, so that V by F is constant. So below rated speed, we will move to constant V by F control. That is, if frequency is reduced to half of the original value, voltage must also be halved so that their ratio remains same. Okay, so that V by F is constant. That way the flux will remain constant, as well as I can reduce the frequency to reduce the synchronous speed. So what is the effect of frequency V by F being constant? So let us first look at Tmax. The expression for Tmax is 3 by omega Sm V1 square by 2x2. Omega Sm is nothing but 2 by P into 2 pi F. That is omega S into 2 pi F. Okay, so there is one frequency term coming here. X2 will be 2 pi F into L2. So frequency is coming in omega Sm as well as X2. So this can be written as 3 by 4 pi by P into 1 by 4 pi L2 V1 square by F square. Okay, so I have separated the voltage by frequency. Since V by F is constant, V1 square by F square is also constant. So the maximum torque remains constant. So as we change the frequency, maximum torque remains unaffected, so it remains constant. Okay, what happens to my starting torque? Because two torques we saw, the most important, that is the starting torque. Starting torque we derive to be 3 by omega Sm V1 square R2 by Sx2 square. Okay, so here there will be one frequency term. Here it will be frequency square. So it is proportional to V1 square by F cube. So it can be written as proportional to V1 square by F square into 1 by F. Since V by F is constant, V1 square by F square is constant. So it is proportional to 1 by frequency. So as frequency increases, starting torque reduces, or as frequency reduces, starting torque increases. Okay, what about the slip for maximum torque? SMT is given as R2 by X2. So it is inversely proportional to frequency due to this X2. So as frequency reduces, slip for maximum torque increases. So now let us look at the characteristics as the frequency is varied. So here if you see, we have maintained the constant maximum torque, and as we reduce the frequency, the synchronous speed goes on reducing. Here F3 is less than F2 is less than F1. And the starting torque, see, F3 is the minimum, but the starting torque in case 3 is highest. Then it is higher than case 2 and higher than case 1, because as frequency reduces, starting torque increases. Okay, starting torque is inversely proportional to frequency. So that is how the characteristics or the torque slip characteristics would look like as we change the frequency in case of induction motor. Now, as I told you, the most desirable characteristics are those in which the torque is maintained constant. So let us assume that the torque is constant. Now, in the operating region, torque is given as 3 by omega Sm into V1 square S by R2. This is the equation for torque in the operating region. Omega Sm will be 3 into 2 pi Ns by 60 S V1 square by R2. 180 by 2 pi Ns into S V1 square by R2. Now, slip can be written in terms of Ns and Nr. So we can call torque as 180 by 2 pi Ns. Slip can be written as Ns minus Nr by Ns into V1 square by R2. Now Ns is proportional to frequency. So here one frequency term, one frequency term. So torque is proportional to Ns minus Nr into V1 square by F square. Since V by F is constant, torque is proportional to Ns minus Nr. If we wish to maintain the torque constant, that means Ns minus Nr should remain constant. Okay, this equation is very important. You must always remember this equation. For frequency control of induction motor below the rated speed, for constant load torque, the difference between the synchronous speed and rotor speed must remain constant as the frequency is varied. Or we can say the slip speed remains constant. Okay, so that is how we control the speed of induction motor, by varying the frequency below rated value. Okay, next let us see above the rated speed. Okay, above and rated. So here we have to increase the frequency. Now flux is proportional to V by F. Here if we are increasing the frequency, we cannot increase the voltage. Why? Because voltage cannot be increased beyond the rated value, otherwise it can damage the insulation of the machine. That is why voltage will be kept at the rated value. So as frequency increases, flux will reduce, due to which I mu will also reduce, due to which no load power factor and full load power factor will increase, as well as iron losses reduce. Due to reduction in flux, iron losses will reduce. Okay. Now let us see the proportionality of T max and T starting again to see the effect on the characteristics. Now first of all, T max, it was 3 by omega S V1 square by 2x2. Now voltage is constant. One frequency term here, one frequency term here. So it is proportional to 1 by F square. So as frequency increases, T max reduces. Then what about starting torque? It was 3 by omega S V1 square R2 by Sx2 square. So it is proportional to frequency square. It is proportional to frequency, so it is proportional to frequency cube. So as frequency increases, starting torque reduces. Similarly, the slip for maximum torque R2 by X2, this is proportional to F, so it is inversely proportional to frequency. As frequency increases, SMT reduces. Now let us plot these characteristics or torque slip characteristics of the machine. See, now we are increasing the frequency here. F3 is the highest frequency and F1 is the lowest. So as we increase the frequency, the synchronous speed in case 3 is highest, then case 2 and then case 1. Okay. So see, the starting torque in case 3 is lowest because starting torque is proportional to 1 by F cube, as well as the maximum torque in case 3 is lowest because it is inversely proportional to F square. So as we keep on increasing the frequency, the starting torque goes on reducing as well as the maximum torque reduces. So this will be the torque slip characteristics of the induction motor above rated speed control. Here the load torque is not constant. So remember, torque is not constant. So now the thing is, how are we controlling the flux? If we see the flux versus frequency, or let us say voltage versus frequency, this is the rated frequency. Below rated, voltage was proportional to frequency because V by F is constant. So it is like this. Then frequency voltage remains constant above the rated speed. So the characteristics should be like this. But if you see, actually when we derived the torque, there it was proportional to E square and not the voltage square. And as we know, the difference between the voltage and EMF is the voltage drop across the series parameters of the induction motor. What are the series parameters? That is R1 and JX1. That means I was neglecting the voltage drop between E1 and V1. That is why I was using V1 instead of E1. But when we derived the torque, we used the EMF instead of the terminal voltage. So if you reduce the frequency, terminal voltage also reduces. But if it goes below a certain value, then we cannot neglect this voltage drop across R1 and X1. So to maintain torque constant or to maintain flux constant, flux is actually proportional to E by F, that is induced EMF by frequency. Okay. So if you go below a certain value, then we have to take care of this voltage drop. So we deviate a bit from these linear characteristics like this. Okay. Because if we go down, then this voltage drop will dominate and we will not be able to maintain E by F constant. To maintain flux constant, this E by F should be constant instead of V by F. So we have to keep V above a certain value so as to compensate for this voltage drop so that E by F remains constant. So remember this thing, that we deviate from the linear characteristic at lower values of frequency to maintain E by F constant. So many times this curve can be asked, the curve between voltage and frequency for frequency control of the induction motor. Moving on to our next method, that is the cascading of induction motor. So here what we do is, we first use a slip ring induction motor or a wound rotor induction motor. Why we do that? Because there are slip rings available in case of wound rotor induction motor. So the other induction motor is supplied through the slip rings of the first induction motor. That is why first motor must be slip ring, other can be squirrel cage as well as slip ring. Okay. So now there are two types of cascading. One is called as cumulative cascading. Other is called as differential cascading. In case of cumulative cascading, the torques produced by auxiliary induction motor and your slip ring induction motor or the main induction motor will be same in direction. Their rotors are mechanically coupled if torque of main and torque of auxiliary have same direction, then it is cumulative cascading. Torque of main and torque of auxiliary have opposite direction, it is differential cascading. So there are two types of cascading based on the direction of torque between the two machines. Now this machine has P1 number of poles, F frequency. So let us say, what will be the synchronous speed of the first induction motor? NS1 will be 120 F by P1. Okay. Assuming that the slip is S1, then rotor speed will be 120 F by P1, 1 minus S1. Now, since we are supplying the auxiliary induction motor at the slip rings, so rotor frequency or the slip ring frequency will be S1 into F. So, synchronous speed for machine 2 will be 120 into S1F by P2. It has P2 number of poles. Because for machine 2 it seems like that the supply has a frequency SF since it is being supplied through the slip rings. So, if we consider the slip of this machine to be S2, then NR2 will be 120 into S1F by P2 into 1 minus S2, that is NS into 1 minus S. So let us assume that S2 is low, which is a valid approximation. It runs at nearly synchronous speed. So NR2 is approximately 120 into S1F by P2 and NR1 is this. Both must be same because their rotors are mechanically coupled. So first let us see the case of cumulative cascading. Here the torques of both the machine will be in the same direction. So their speeds will tend to be in the same direction. NR1 equal to NR2. That means 120 into F1 or 120 into F by P1, 1 minus S1 should be equal to 120 into S1F by P2. Okay, that means P2 minus P2 S1 should be equal to P1 S1. So S1 is equal to P2 by P1 plus P2. So if we find the rotor speed, 120 F by P1, 1 minus P2 by P1 plus P2. This will become P1 by P1 plus P2. This will get cancelled out. So it will be 120 by F by P1 plus P2. That will be the speed of the set. Speed of the set means the speed of the two induction motors. Since their rotors are mechanically coupled, they will rotate at exactly same speed. What happens if we do differential cascading? Then the torques are opposite. So that means if one motor tries to rotate in clockwise direction, other will try to rotate in anti-clockwise direction. So we will say that NR2 is equal to minus NR1. Actually the speed is same for both the machines due to rotor coupling. But their natural tendency is to rotate in opposite directions. But we are forcing them to rotate in the same direction. So here the speeds that we are talking about is their natural tendency, that is opposite of each other. So we will say 120 into S1F by P2 is equal to minus 120 into F by P1, 1 minus S1. Okay, so minus P1 S1 is equal to P2 minus P2 S1. So S1 will be P2 by P2 minus P1. So rotor speed will be 120 into F by P1, 1 minus P2 by P2 minus P1. Okay, so this will be 120F by P1 minus P2. That is the case for the differential cascading. That will be the speed of your first induction motor. So the speed of second will be 120F by P2 minus P1 because both are opposite of each other. Okay. Now what happens? Since we are supplying the second induction motor from the slip rings of the first induction motor, so the input of second induction motor is actually SPG, that is the slip power of first induction motor. Okay, so it is also called as slip power recovery scheme. Okay, and mechanical output of first motor will be 1 minus, let us say S1 into PG1. Okay, why it is called as slip power recovery scheme is because we are recovering the power output at the slip ring terminals to drive another induction motor. Otherwise, if we do not connect any load at the slip rings, this power gets wasted. So here I am recovering this power and making it useful. Otherwise, it gets wasted as the rotor copper loss. So the ratio of mechanical power to electrical power will be 1 minus S1 is to S1. Okay, so 1 minus S1 would be, this will come out to be P1 is to P2. So the ratio of the number of poles indicates how much slip power I can recover from the first induction motor to drive the second induction motor. That is also called as slip power recovery scheme, or we can say cascading of two induction motor. Slip power recovery scheme. Okay, so this is also one of the methods for control of the speed of the induction motor. Okay, so these are all the methods that we have studied till now for the speed control of induction motor. We saw 3 methods for slip control technique and 3 methods for the synchronous speed control. Now let us move on to the braking. So we have started the motor, we have controlled the speed of the motor. Now it's time to stop the motor from rotation. That is, we have to apply brakes on the induction motor. So the braking that I am talking about here is electrical braking. Anyways, if we apply the mechanical brakes to the shaft of the machine can be braked. But we want to decrease the speed in terms of electrical braking. So the first method that comes to mind is regenerative braking. So to brake the induction motor, we have to reduce the kinetic energy of the motor. To reduce the kinetic energy, we must extract that kinetic energy. Either you must dissipate that energy, or you can convert that stored kinetic energy in the rotor of machine to electrical power output of the machine. So if we can convert the stored kinetic energy, that is mechanical energy, into electrical energy, then kinetic energy will reduce and speed will reduce. So what to do is to operate the motor in the generating region. If we are converting mechanical to electrical, that means the machine is working as a generator. So we have to make the induction motor behave as a generator. So we saw 3 modes. When slip lies between 0 and 1, it was motoring mode. Slip less than 0, it was generating mode. And slip greater than 1, it was braking mode. So here we must operate in the generating mode. Slip is equal to ns minus nr by ns. If nr is greater than ns, then slip is less than 0. So we have to somehow make the rotor speed greater than the synchronous speed. How to make the rotor speed greater than synchronous? It can be done by reducing the synchronous speed. Okay, suppose rotor is rotating at 500 rpm and synchronous is 600. Suddenly if I make the synchronous speed to 300 rpm, then rotor is 500, but the synchronous speed is 300. So the rotor speed is higher than synchronous. It will start operating as a generator, and that is how when it will convert the stored kinetic energy to the electrical energy. So how to reduce the synchronous speed? So 120 F by P, that can be done by increasing the number of poles or by reducing the frequency. To increase the number of poles, we can use pole changing technique. but that is only applicable in case of squirrel cage induction motor. That is, I will bring out the stator winding terminals and I will connect them so as the number of poles double. If the number of poles double, synchronous speed will be reduced to half. But if I have an inverter or a cycloconverter, then what I can do is I can change the input frequency to the motor. If we reduce the frequency, then the synchronous speed will go down, and then the synchronous speed will become lower than the rotor speed. So these two are the methods to control the synchronous speed. So now when the synchronous speed goes below the rotor speed, the rotor will start to decelerate. But as soon as rotor speed again becomes less than synchronous speed, slip becomes greater than 0, it enters motoring region. So it will start operating at the new rotor speed. So that means as soon as rotor speed goes below the synchronous, we must switch off the supply. Otherwise, it will again start operating as an induction motor, but at a new rotor speed which is below the new synchronous speed. So we must take care that we switch off the supply before it enters the motoring region again. Okay, so that is the regenerative braking. Next method is called as plugging. Here we will operate the motor in the braking region, that is S greater than 1. For S greater than 1, NR and NS should be opposite. But the rotor speed cannot be reversed. Why it cannot be reversed? Because rotor has inertia, so we cannot reverse the speed instantaneously. But we can reverse the direction of rotation of stator magnetic field. To reverse the direction of stator magnetic field, we have to change the phase sequence. So if the phase sequence is ABC, I change it to ACB, the rotation direction of stator magnetic field reverses, which can be done by interchanging the two terminals B and C. If we interchange these two terminals, stator magnetic field reverses, and then the slip will become greater than 1. If the stator magnetic field is rotating anti-clockwise, then the natural tendency of the rotor is to follow the stator magnetic field. So it will also try to rotate anti-clockwise. So suppose initially stator magnetic field as well as rotor are rotating in the clockwise direction. Now when we change the phase sequence, the stator magnetic field will start rotating in the anti-clockwise, that is in the opposite direction. So the rotor will tend to follow the stator magnetic field and rotate in the anti-clockwise direction. So to rotate in the anti-clockwise direction, the torque will be reversed. That is why during plugging, the torque has been shown as negative. Why negative? Because the torque is reverses in direction, then the torque will become negative. The total torque, as I told you in the operating equation for a motor, Tm minus TL. So the total torque is Tm minus TL. This is my Tm. This is my TL. TL is the torque before plugging, because before plugging in steady state, Tm will be equal to TL, so that the speed of the motor is constant. In steady state, motor torque and load torque are constant. So the characteristics before plugging will indicate load torque, and the ones after plugging will indicate your motor torque. The difference between the two, load torque and motor torque, will give me braking torque. Okay, so plugging torque is this. This is my load torque. The difference between the two will give me braking torque, because this is the difference that will determine the acceleration and deceleration of the machine. So the rotor will start decelerating, but then since the field is rotating in the opposite direction, it will start rotating in the opposite direction. It will try to follow the stator speed. That means I must switch off the supply as soon as the speed is near to the zero speed. Otherwise, rotor will start rotating in a direction opposite to the initial value. So it will start rotating in reverse direction, that is the direction of rotating magnetic field. So you must take care to switch off the supply before such a thing happens. Next type of braking is called as dynamic braking. Here what we do is, we will switch off the supply. Supply is switched off, and then we connect a DC supply across stator. What is the function of DC supply? It creates a stationary magnetic field. Okay, but rotor is rotating. So that means there is relative motion between rotor conductors and your stator magnetic field. Due to relative motion, there will be EMF, and induced EMF opposes the cause of induction. Cause of induction is relative motion. So it will try to oppose the relative motion. How it can oppose the relative motion? By bringing the rotor to a halt. So rotor speed will start reducing. Okay, then only it can reduce the relative motion or reduce the relative speed between the stator magnetic field and the rotor conductors. That is called as dynamic braking. Okay. So let us summarize what we learnt in this lecture. We first saw frequency control. So we saw when speed is to be brought down below the rated speed, we keep V by F as constant so that flux does not saturate. And here for constant torque, we have Ns minus N as constant. For N greater than rated speed, only frequency is varied, that is pure frequency control. So here maximum torque was proportional to frequency square, starting torque was proportional to frequency cube. So as frequency increases, starting torque as well as maximum torque decreases, and load torque is not constant. Then we saw cascading. In cumulative, we had speed as 120 F upon P1 plus P2. In differential, we had 120 F over P1 minus P2, where cumulative is the one in which the torques of auxiliary as well as main induction motor are in the same direction, and differential is the one in which the torques are in opposite direction. Then we saw the braking of the induction motor. First method was regenerative braking, in which it was operated as a generator by bringing the synchronous speed below the rotor speed by controlling the frequency or by changing the number of poles. The other method was plugging, in which we operated the motor in the braking region by reversing the direction of stator magnetic field by reversing the phase sequence. And the last was dynamic braking, in which we applied the DC supply across the stator to create a stationary magnetic field which cuts the rotor conductors and effect opposes the cause, so rotor speed is brought down and then the rotor comes to a rest. So that is what we learnt in this lecture. In the next lecture, we will solve some problems based on torque slip characteristics and speed control of the induction motor.